It is too cold, too snowy, and just generally ugly in the Oregon high desert right now. So I'm not flying my glider. I'm fooling around with technology stuff. And I thought I'd share a little bit about what I've been playing with. Recently on YouTube, I came across a bunch of videos about using linear CCDs, which are an interesting part with a interesting history that I'm not going to talk about right now. But they're just they're very cool little devices, and people have done some neat stuff with them on YouTube. In particular, I very much enjoyed this series by this curious scientist person who did a great job sort of explaining the fundamentals and going through how he got his device working and turned it into something useful. And that kind of inspired me, so I don't want to watch it. Um, I went ahead and went to uh, eBay and started looking for CCD devices. And this TCD 1304. That's what a lot of the people on YouTube have used, and that's pretty cool. Um, but then I found this Sony device for sale, which is this is a 3800 pixels, and this is 5000 pixels in essentially the same package size. I was like, oh, more pixels, more better, and and it was something different, and so I went ahead and ordered a couple, and so now I have to um, figure out how to drive it, how to make it give me some output that I can play with. And so for that, um, I'm going to kind of copy a little bit what everybody else has been doing in that I'm going to use a STM32 part. People use various different ones from nucleo boards to Bluepills to what I'm going to use, which is what's called a Blackpill, which is an STM32F4 core with a minimal board around it. And actually, here's a picture of what that looks like. So right here is the microcontroller unit in the middle, and the just very basic development board around it. I've stuck it on a breadboard after I soldered the pins onto this little board so that the pins don't short out on anything on my desk. And I plugged it into what's called an ST link. This is not from ST. This is a Chinese knockoff, and a cable that I made myself with a bit of electrical tape and some jumper wires. And so this lets the my computer, whichever computer I'm using to program it, download a program into this microcontroller and get it running. It also lets us do some real-time debugging, which is pretty neat. Anyway, um, that's what we'll be playing with. So let's take a look at the data sheet for this ILX-501. So it's a linear CCD sensor, um, and it has ratings for voltage, and the data sheet tells you how to handle it and what the maximum clock rate is and what the pins are expecting. So this is sort of a block diagram of the internals and how the pins are sort of connected from the outside of the package to what's going on inside, and descriptions and voltages. And anyway, what we need right now is the sort of the timing diagram of what pulses we have to send in, which is these two pulses, and what is going to come eventually. We'll worry about what's going to come out of the device, which is this stuff. But for now, you can see that we basically have one pin that we're sending in a a square wave clock signal, and it goes in, and then at some point we do this reset pulse song and dance, and then there's this other pin that is involved in that reset pulse. It's called the reset gate up here. You can find it up here. It's ROG right there. So anyway, and this is the details of those clocks. So the first clock that, or the first signal that we want to get running is the just the basic. How are we going to drive it? So this this clock pin can be says minimum 100 to max to typical 200 to maximum, undefined nanoseconds. So 200, that's basically the width of half of the pulse. So 200 would be 400 nanoseconds per cycle, which is a little 1.2-ish, or 1 point, whatever it is, 1.6 megahertz. 100 would be 200 nanoseconds, which would be 5 megahertz, I think. Anyway, we're going to go for a 1 megahertz square wave, which will mean that each half of this is 500 nanoseconds long, and the duty cycle is close to 50%. So it says here the duty cycle needs to be between 40 and 60%. So as long as we're around 50, we'll be good. So that's what we need to figure out first. So let's get that out of the way with our little microcontroller board. Let's get it making us a 1 megahertz pulse. So this is the IDE from ST, which is okay. It works. It does some neat stuff. So let's make ourselves a new project. And we're going to make a new STM32 project. And it's going to grind away and pull up a target selector, and we'll plug in our part number, which is an STM32F411ceu6. Oh, wrong place. STM, what the heck? What is going on with this? 32. Wow, there's something seriously borked on this. F411ceu6. All right, well, I don't know what's going on with that search box. It's weird. Here's our part, and we can hit next. And then just give it a name that puts it at the end of my projects list. XX driver test. Okay. Okay, so here's our configurator for our part. This lets us set up the various internals on our device and translates our graphical setup here into configuring the various registers on the device to do what we want it to do. So the first thing we need to do is tell it to use the external crystal so that we can drive it at full speed. And that's good. And then we're going to go here to the clock configuration, and you can tell it how fast you want it to run, and it defaults to something low. So we're going to run it at 100 megahertz, and it's going to, grind around and figure out how to do that. Okay, come on. Okay, it's there. And now we got to think about putting out our 1 megahertz square wave. Well, these STM parts have these really neat peripheral called a timer peripheral, and we're going to use that. So we're going to use our timer 1 in PWM mode, and we'll use channel 1. And now we have to tell it how to generate the pulse that we want. So we're going to go here to we're going to make a couple of constants. So the first constant we're going to define is how many ticks per second is our system clock running at. So our system clock, hardware clock, is running at 100 megahertz. So it's generating 100 million ticks every second. And the second constant we're going to define is how fast we want our clock to run. So right now we're shooting for 1 megahertz. So we'll say this is called ILX clock, and we're going to define it as 1 megahertz, 1 million ticks per second. So now we can go back to the parameter settings, and instead of typing in a number here, we can say our hardware clock is running at 100 million clicks per second, and we want to end up with 1 million clicks per second. Well, by common sense, that would be 100, right? However, if we do it this way, and then because of the way the clock setup works, we need to subtract 1. So if we do it this way, we should end up with, we will end up with defined setup, so that when we decide that we want to run it at 1.5 megahertz or 500 kilohertz, all we have to do is change that define, and it will generate a nice default, or it will update our timing parameter to reflect our new desired ILX clock timing. So the way PWM generation works with these timers is you have one register that basically the timer just counts every system clock tick. So it's counting along at 100 million ticks per second. And so we're going to tell it to count for 100 ticks. That gets us to 1 microsecond. And then reset. So this counter period is set by something called the auto reload register, which you can see that's this here. And so what that means, that auto reload is talking about, is it counts up to whatever value you have in the auto reload register, the ARR, And when it gets to that value, it resets to 0 and starts counting again. So that sets our period. And then in between that, so the second thing that we talk about is this pulse, and this is the sort of capture compare register. And so what happens is, as it's counting up, when it passes the pulse count or the CCR register, it changes the state of the timer from the default state to the active state, or vice versa, depending on how you have this polarity set. So we're going to set our pulse to be half of our period. So this is going to be the 100 million divided by 2 times ILX clock, and then that minus 1 for the silliness with the timer. So there's that should get us a pretty close to 50% duty cycle square wave. So let's see how that worked. Let's save, and we're going to generate code. And then here we're going to go into our project files and our source files and look at our main.c, because there's one thing we have to do here. So this is automatically generated, and it comes in, it sets up the timer 1 variables, it initializes the system clock so that we have a delay function available in the hardware abstraction layer library, and it initializes our timer and our pins on the chip. What it doesn't actually do here, which was a surprise to me, is that it doesn't actually start the timer. You have to do that yourself. So we have to do, after it's been initialized, and before we go into our infinite loop, which is this while one loop, we need to start the timer. So we're going to do how tim pwm start, and we're going to hit control spacebar, and we'll find a couple of different versions. There's tim start IT, which is to start the timer and have it generate an interrupt when it's done each pulse. Or we could have it start to do timing for the DMA, direct memory access handler, which we're not going to do. And so we just want the start with no extra bells and whistles. So there's our start, and then it helpfully gives us the option to choose our arguments. And so this channel is going to be tim channel, and then control spacebar, and we can choose our channel 1, which is what we configured in the configurator. Seems a little redundant to have to do all that, but there you go. Put a semicolon on it so we don't look like a fool. Save it, and let's run it. Alright, this is the first time we'll set up our SD link. Hit OK. Alright, there we go. It's connecting up to the debugger and downloading, and there we go. Should be running. So how are we going to take a look at that? Well, I have a handy little software, well, software hardware combination logic analyzer that is this nice little device. I like it a lot. There we go. It's found its hardware buddy, and here we have a capture session ready to go. And when I was getting started, I hooked up the logic analyzer, but just to see how I'm going to hook that up, let's go back to the IDE and look at this picture of our device. So here it tells us that our timer 1, channel 1 is coming off of PA8. So let's make our logic analyzer reflect that. So I hooked the first channel up to that, and this is going to be our ILX clock, and that was on PA8. It's just how I like to keep it organized. Let's run a capture, see what we get. All right, well, there's a signal here. And zoom in, and we can see that it is, well, it's 1 megahertz, and it's not quite 50%. And it's 48 and 52, and that's probably because of some silly integer math thing that went in with our defines. If we directly define the pulse and ARR period, we could make this pretty much exactly 50-50, but I'm not going to worry about it because the way I've got it set up makes it easy. So there's a 1 megahertz clock. Great. Now what? Well, now we need to go back to the datasheet. Okay. So this is this part handled, and the next thing is this song and dance around the reset. So how are we going to figure out when to do this? We could figure out a time delay and just fire off a reset pulse on after a given time delay, and that's essentially what we're going to do anyway. But we could base it off of the hardware clock on the STM32. But what we really want to do is the ILX-501 CCD is going to give us 5,036 pieces of useful information, and then it's going to give us garbage. So after the reset pulse, we want to count. There's going to be useful information for 5,036 clocks, and then there's not going to be. So why don't we just count this clock and count out some number more than 5,036, and then do a reset based on this clock. So that's what I'm going to do, and I'll show you how to do that. So let's say we're going to go every 5,200 of these. So we're going to go 5,200 microseconds before we send out a reset pulse. All right, let's look at our IDE. So to do that, we're going to have to use our timer 1 to send out a master signal. So right here, we want to enable trigger. And the trigger signal that we want to send out is based on the update. And when that is, the update event is what happens every time it gets to the end and resets the auto reload. And it resets when it hits the auto reload register count. So that's the update event. And then we need to transfer that update event to the next timer. So let's look at how to do that. We're going to start up with timer 2. And it's going to be in slave mode, and it's going to be clocked from this external clock. Okay. And it's going to have a trigger source, and there's all these choices. And what are all these choices? So ETR is external trigger, which can be a pin. If we pick that, we'll get a pin show up on the device that we can send an external trigger in. That's not what we want. So we need to look at the documentation, and the documentation we need to look at is here. We need to look at this reference manual 383, and this is the F411 reference manual. This tells you how all of the internal bits are wired together on our particular device. And what we're interested in is timers, and we're looking at, for this table right here, the internal trigger connection. And so if we look here, this slave timer is timer 2, and we're looking for the output from trigger 1, time 1 trigger output. So that is available to us on ITR 0. Okay, that's pretty cool. And I'm looking for a little, what's it? Functional description. Yeah. Timer synchronization. This is kind of cool. Using one timer as a prescaler for another. That's exactly what we're doing. So we're taking time 1. We're outputting the update event from time 1 onto trigger output. And it goes into across ITR 0 and comes into time 2. And time 2 needs to be put in slave mode, and then it goes ahead and counts these pulses the same way time 1 is counting our system ticks. Okay, so yeah, this actually describes how to do it in some amount of detail. It tells you about writing to the registers and setting up the registers to do it. Well, by using the IDE and the graphical configurator, that is what those are doing when we click the buttons in the IDE. Ultimately, it generates code that accomplishes these processes, or this set of steps. So let's go to the IDE and make that happen. So we need ITR 0 as our external clock coming into timer 0 or timer 2, and we want to generate output on that. So let's generate a PWM output, and that's going to come off on a pin on the part. And now we can look at our configuration. All right, so this is what we want to set. We want to set this to be 5200 pulses. Whoop, not 6200. How about 5200? All right, and so the way PWM works is it starts counting up, and when it gets to this number in the auto reload register, it updates itself back to 0 and starts counting up again. And the pulse generation happens when it counts up to the pulse time. So we'll just say 4 here. To give us a 4, this should give us a 4 microsecond length pulse to see. And, well, 4 minus 1. Minus 1. There we go. So that should, I think that should give us a 4 microsecond pulse. And this should be 5200 minus 1. Just like in the other one where you have to do this minus 1 rigmarole to account for the fact that it's starting from 0 and not 1. Okay. So now our pulse should go for 4 ticks, and our counter period should be 5200 ticks. That seemed pretty simple. Okay, let's generate code. Generate code, and now just like last time, we need to go into our main C file. And now instead of starting timer 1, if you look up here, we've now generated initialization code for timer 1 and timer 2. And if you look at if you right click on this, we can jump to the declaration, which is further below in this file. And you can see that in the initialization, it's setting up this data structure that it's going to feed into the registers. And so this is exactly what we said. We're timer 2, counting up. We're going to do 5200 minus 1 for the period, the ARR. And then further down here, we see that we're in slave mode and it's coming off of our ITR 0. And a little further down, we see our clock output compare setup, which is our pulse. And that's 4 minus 1, just like we did in the IDE graphical thingy. So now back up here where we started. Here's where we started timer 1. So we just need to start timer 2, and I'm just going to copy this and paste it and change this from timer 1 to timer 2. And they're both using channel 1, so that's good. And save this and run it. Well, wait, before we run it, let's look at what pin we're getting. So timer 2 channel 1 is coming off of PA0. So I'll connect my logic analyzer to PA0, and when we run this, there it goes, download it to the device, and it's running. Go over to our logic analyzer, and we can say this is our, let's call this a synchronization sync pulse, and it's on PA0. Run, capture. Did we get anything? Remember, there it is. So 5200 microseconds apart, plus or minus a little bit for the pulse length. All right, there we go. So it's counted 3 ticks, not 4. Anyway. I think I might have that whole jazz with the -1 not quite right. Let's go back to the IDE and see if we get a different result on the let's take this 4 minus 1 off of here, and this 5200 minus 1 off of here, and in timer 1 we're gonna stop doing this -1 jazz till I understand it better at another time. I'm just copying what somebody else did, and they seem to think that was important, but it's not doing what I expect, so I'm gonna project, generate code. Let's run it. See what we get here. So before we were getting 480 and 520 nanosecond pulses, and this was 3 microseconds. So let's look at what we're getting now. Find a reset pulse. That's 4 microseconds, which was what I was expecting, and this is 520 and 520. Well, it's still it's 1 megahertz, and it's more like 50%. Anyway, okay, I like that better. All right, now we've got a sync pulse. What are we going to do with that? Let's look back at the datasheet. So the song and dance for the reset goes like this. There's a reset pulse on the clock pin that goes high, and then it waits T7, which is at a minimum of 100 nanoseconds and normally 200. So we'll just go with 200. So it waits 200 nanoseconds. And then ROG goes high, and it waits T8, a minimum of 800 and typically 1,000 nanoseconds, so 1 microsecond. And then ROG goes low, and it waits again T9, which is 200. So 200, 1 microsecond, 200. So we have 1,400 nanoseconds total in this clock pulse. Okay. And we want that to kick off every 5,200 microseconds based on our current clock. So our 5,200 clock ticks. And we don't care what the actual time is because we can set our clock to be what we want. So, cool. Here's how we're going to do that in our device. So, we're going to use another timer peripheral. Timer 3. And it is also going to be in slave mode, but it's going to be in trigger mode. And we'll get to that. And it's going to be in PWM generation as well, but it's going to be in 1 pulse mode. And the trigger source, well, we want to trigger based on timer 2. So let's go back to timer 2. We need to generate some triggering output. So this master slave mode needs to be enabled. And we want to enable on our update event. So when the trigger triggers and finishes its count, then we want to generate an update event. Or it's going to generate an update event, and we want to pass that on to the next guy. So the next guy is timer 3. And we need to go back and look at that table. So table 53. So we're looking at timer 3 as our slave, and we want timer 3 to look at the output of timer 2. So that is ITR1. Great. So we're going to, trigger source is going to be ITR1. And so what's going to happen in this trigger mode and one shot is when this trigger comes in, it's going to start the counter counting. And it's going to count until it gets to an update event. It's going to reset to 0, and it's going to stop until it gets triggered again. So we just get 1 pulse out of it, and we get to shape that pulse. Now, we said that we wanted 1400 nanoseconds, and I could do the jazz with the dividing out the hardware clock, but honestly, I'm just gonna type this in. And the reason is because the hardware clock may change a little bit because I have to change the clock settings when we get to doing the USB, but it's not going to change very much. And the pulse width on these the acceptable limits on these pulses are such that if it gets a little longer, which is going to happen if my main clock slows down a little bit below 100 megahertz, then nothing's going to be wrong. So I can just hard code these and change my clocks as I change them, and it's not gonna make any difference. So the key point here is these don't depend on the ILX clock, and so we can just set them the way we want them. And so this is going to be a 1400 nanoseconds. It's going to go high after one tick, and the CH polarity, we're going to say this is basically where it starts. So if you have this on high, it starts at high and goes low, and if you have it as low, it starts at low and goes high and then goes back to low when it's done, which is what we want. So there we go. Let's save that and generate code, and then we need to go and start this, and it's a little different starting this guy. Generate code. I'm making a screen capture to describe what I was doing with this driver. Now I'm going to have to cut this out of the screen capture. People wondering why I'm sitting in the dark and talking to myself. Okay. So now we need to go to the main file, and we need to start the timer. So we look here, we've got our timer 3 has been configured, and it's actually useful to look at this init function. So let's just jump down there for a second. So for timer 3, it's the same sort of stuff that we saw, but this operation mode is now going to be in 1 pulse instead of PWM. And that ends up being important. So we'll just keep track of that. Why that's important is we can't just copy this timer start. We got to start it as a 1 pulse instead of a PWM. So Hal Tim 1 then 1 pulse start. So we've got 1 pulse start and 1 pulse start IT. So a start IT starts it and registers an interrupt so that it generates an interrupt when it finishes, and we can use that to do other code by writing our own interrupt service routine to handle the interrupt call. But we're not going to do that right now. That's a bell and a whistle that we don't need. So we're going to go here and we're going to start timer 3, and it's still on output dim channel 1. Put in a semicolon so we don't look like a fool. And save. And what pin was this spitting out on? This is spitting out on timer 3 channel 1 PA6. run. Get that logic analyzer hooked up to PA6 on the third channel, and we can go over here, and this is going to be our clock reset pulse, and it's on PA6. There we go. We got a pulse. Let's see how long it is. It is 1.4 microseconds, 1400 nanoseconds, and it followed along after the sync pulse. So great. Okay. So now, same rigmarole. Back to the data sheet. Let's look at our next pulse. Is going to be this ROG, the reset gate pulse. And so this one has to start T7, which is 200 nanoseconds after the first pulse, the reset pulse, or the clock reset pulse. And then it goes high for 1000 nanoseconds, and then it goes low, and we're done. Okay, so the key thing is this. The whole period of this is 200 nanosecond delay plus 1000 nanoseconds of high. So we're going to do 1200 nanoseconds. So timer 4. It's going to be the same like timer 3, triggered. Trigger source is ITR1. Channel 1 is going to be PWM generation. And how long the total length of that pulse is the 200 plus 1000. So 120 ticks. And it's going to go high after one tick. No, it's going to go high after 200 nanoseconds, which is 20 ticks. All right. And yep, it is. That I think should be it. Generate code. So this guy is going to be putting out, this is channel timer 4. Timer 4, channel 1 is coming off of PB6. Let's just get that channel 4 of the logic analyzer hooked up. Okay, PB6. And then go to our main and get this one started as well. So we can start it just like we started the last one. Copy, paste, channel 4. Save, run. Have a look at what the logic analyzer is showing us. Run. I forget how to make it sync on whatever. That is not right. We're getting a pulse every time. We must have got our ITR, our channel select wrong. trigger mode. Timer 3 based on timer 2's trigger output is ITR1. Timer 4 based on timer 2's output is ITR1. Don't quite know what was going on there, but oh, I know what's going on. Duh. Dang it. Let's do that again. Trigger ITR1. What didn't I set? I didn't set this one pulse mode. So it was configured to run in PWM continuously. So we've got 120 and 20 and generate code. Shouldn't have to change anything in the main. Fire it off. And I can't remember how to make it trigger on. There's a way to make it so that this shows up right in the middle. Anyway, oh, what did we do? We didn't set the polarity. So it starts out high and goes to low instead of starting out low and goes to high. However, the timing looks good. Let's go fix that. Knucklehead. Polarity. Start out low. Save. Generate. Okay. Hopefully there we go. There's a pulse. Goes high for 1 microsecond, goes low, and it waits for .200 nanoseconds before it goes high. Okay, that's pretty cool. So we've got all of the pulses being generated that we need to make our device run. Now, how are we going to use these on to drive the device? We're going to take this clock reset off of PA6 and the ILX clock off of PA8, and we're going to OR them together. And by doing that, we've got our clock ticking along, but when this goes high, when either one of these is high, if they're ORed together, then the output is high, so we'll get our reset pulse, and then it's going to go low. And if the reset pulse happens to end while the clock pulse is high, that's okay, because if we look at the data sheet, the spec on that reset is that it can be as long as it wants. So this T9, which is how long it waits after ROG, has to be a minimum of 100. Typically is 200, which is what we've got set up, but it can be as long as it wants. Maximum is undefined. Okay, so that is how we get our 3. That's how we're going to get our driver to our clock circuit. We're going to, the other thing that we have to consider is that the device, all of these inputs are 5 volts. So every one of these inputs needs to be the clock pulse. If we look here at the specifications, the high level needs to be minimum of 4.5 volts, typically 5, and the low level needs to be close to 0. And so our 3.3 volt logic coming out of our microcontroller is not going to drive this happily. So we're going to have to take the 3.3 volt pulses and turn them into 5 volt pulses. And so it just is a happy coincidence that we need to OR 2 of those signals together. So we'll take an OR gate and set it up so that it takes its input happily from a 3.3 volt and spits out 5 volts on its output levels, and will be golden. And then for the reset gate, we can just feed it into an OR gate and have it generate basically the same output. And we can tie one of the OR gates to inputs to low, and then it's just going to mirror whatever it gets on its input onto its output, but it's going to put the output at 5 volts. So planning ahead for how we're going to drive this, drive the part. So in this data sheet, they give us a nice sort of how do you wire it up. So it needs a 9 volt power supply, a 5 volt power supply, and then it takes from the output, we feed the output into a current buffer using a transistor, and then we'll take our output signal. We'll do the A to C conversion based on this output signal. So that's pretty cool. I will talk about that next, but I think we've got a good enough bit for now, and so I'm going to stop talking.